All right, so let's get into actually fitting a line to our data. So line of fit, that's what we're going to deal with. We're going to draw lines of fit into our data that we graph. And a line of fit is a line that fits the data reasonably well. Sometimes they call this the line of best fit as well. Okay, and there's an exact line, which we'll talk about briefly today, and we'll actually do a project on this. There's an exact line that we call the linear regression line. And we'll look at this on our calculator today, but as of right now, we're just looking at just a line of fit that kind of fits our data. So I got 3 graphs here. Let's take a look at A over here. So I'm trying to draw a line that fits this data. Okay, well, first things first, your line does not have to go through the origin and then come up, right? It doesn't have to go through the origin every time. You just have to fit your data. And is this a line if I just connect the dots here? No, lines are straight. Okay, so we want the line that's like kind of the average of all the points. Well, if I kind of went along these points, that makes a line. I agree. Does that fit my data? Well, it's pretty good. I got 2 more points above and 1 point below, so that's not bad, but I could probably do just a little bit better. I would say it's more so along the lines of somewhere in there, kind of right in the middle, right in between. It should be like trending the way your data. If you did the line that I just did before, that's probably pretty good, but we want to be as best as we can. So there's my line. I'm going to go ahead and do it for each one. So if I do it for B, so now it's going down, so it has a negative slope, so it's somewhere in about right there. I should have about the same amount of points above the line as below the line. And same thing for C, I have another negative slope, and it's kind of coming about, just right there. I'm just doing my best, drawing my best line that I can. Well, I can also write an equation for these lines. And let me look at this blue guy. I'm going to write an equation for this one. I'm going to say y equals, something in slope-intercept form, like mx plus b form. Well, what do I need to know? I need to know the slope, and I need the y-intercept in this case. Well, I can find the slope by finding 2 points on my line, and then I plug in, and it takes a little bit of a process to find the y-intercept. So there's actually a quicker way to write an equation for the line, and that's by using point-slope form. So that basically just means if I know a point on my line and I know the slope, I should be able to write an equation for the line. And these are both point slope form. The one over here, this blue one, is just m is representing the slope, whereas the green one over here, b is representing the slope. So the blue is for like slope-intercept form, and the green is for strictly intercept form. And this is the way the book will do it. Okay, but they'll also do it just a little bit different. So think about this. All of your equations are y equals, right? Y equals. So in this case, this point slope form over here, it says y minus y1 equals m times x minus x1. Well, that x1, y1, that just represents a point on your line. So that point that's on your line, that's represented by x1, y1. That's just some point on your line. It could be any point on your line. So we need to plug values in for those. Well, let's go back to this point slope form in the blue. So I want to get this y by itself right here to write an equation. So I need to add this y1 over. So y equals, m times x minus x1 plus y1. So that's another way I can write my equation. Same thing over here. I can say I can add the y1 over, add the y1 over. So I can say y equals b times x minus x1 plus y1. So just 2 different ways to write it. One, remember, m and b, they both represent slope. Okay, I'm going to use m just because I like m for slope instead of b, because I like the b being the y-intercept. So I'm going to look at this equation over here, and I'm going to look at it in this form just because I already have my y by itself. Okay, so if you can remember, slope times x minus x1, and then add the y1. So I'm going to use that. So I'm going to go ahead and write it back on my last screen. So y equals slope times x minus x1 plus y1. So that's going to save me some time. So can I find a point on this blue line really easily? Yeah, we usually to find points, the easiest one to find is to look for the y-intercept. Well, where does this graph cross the y-axis? Right here. So that's at the point 0, 8. So basically, I can plug that point in for 0 would go in for x1, 8 would go in for y1. So I'm going to plug this 0 in for x1 and this 8 in for y1 up here and see what happens. So I have m times x minus 0 plus 8. Well, what else do we need to know? We need to know the slope. So how do I find the slope of this? Well, I need to find another point that's on this line. And I'm going to pick one that's, right on a grid, so it's nice and easy. So here's another point. That's at what, 5, and it's up 4. So for me, I could use my slope formula. I could subtract my y's on top, 8 minus 4, and subtract my x's on bottom, 0 minus 5. I like to just count, so I'm going down 1, 2, 3, 4, down 4. So that's a rise of negative 4, and right 1, 2, 3, 4, 5, positive 5. So negative 4/5 is my slope, so I'm going to put that in for m over here. So y equals negative 4/5. Okay? Well, and what is x minus 0? That's just x, correct? So I could just replace that with just x. And there's my equation. Y equals negative 4/5 x plus 8. And I just wrote it in slope-intercept form for that equation. So what I did was I wrote an equation of a line for my line of fit right there. And that's important. We need to know how to do that. So basically, all you need to know is the slope and a point, right? So then we can use point, slope, form. So let's just do one more using point, slope, form. It says write an equation in point, slope, form through 4, 3, and negative 2, 9. So what are the two things you need to know? A point on the line. So I have two to choose from, either 4, 3 or negative 2, 9. And I need the slope. Well, we better find the slope right away. So m equals, subtract my y's on top. So I'm going to go 9 minus 3 on top. Subtract my x's on bottom, so negative 2 minus 4. And we have 6 over negative 6, which is negative 1. There we go. And then what's my point slope form? Y equals m times x minus x1 plus y1. So then we plug in, well, which point do you want to pick? I'm going to pick 4, 3. All right, so I got to plug in 4 for x1 and 3 for y1. And then I need negative 1 for my slope. So y equals negative 1 times x minus 4 plus 3. And now let's simplify. So y equals, distribute my negative 1, so I got negative 1x plus 4, right? Because negative 1 times negative 4. And then I still have my plus 3, so y equals, well, negative 1 times x is negative x plus 7. So there's an equation for my line right there. Write an equation in point slope form. So your book, your answers are going to leave it just like this, and that's totally fine, right? We're just plugging in. So you can just plug in, but I wanted to solve it all the way through just to show you that I could write it nice and neat as an equation of a line. Okay? So let's use this now, the wave. So we all do the wave at sporting events, right? So I got some data on the wave here. The number of people and the time it takes to complete the wave. So what we're going to do, we're going to make a scatter plot on our calculator, and then we're going to find an equation for the line of fit here. So let's grab our calculators, and let's plot in our lists here. So I go to Stat, Edit, and I already got all my lists typed in. So make sure they line up. So 2 for list 1 should line up with 2.1 for list 2. Same thing, 5, 4.4, right? So maybe type in that first list all the way through, then go back and type in the second list and make sure they match up. So 15 goes with 7.5, okay? So make sure they match up. When you're done, we want to make a scatter plot. So we go into our stat plots. So second y equals button. And I want to turn one of these on, which is on. Then I go. So here's the scatter plot. We don't want the line with it. We want just a scatter plot. And then X list should be L1, right? Because if I think about this, we'll talk about that in a second. So watch probably look. Which one depends on the other? Does number of people depend on the time, or does the time depend on the number of people? Yeah, time depends on the number of people. So the time should be my Y, and the number of people should be my X, which is the independent. Remember, always look at that. Which one depends on the other? So list 1, that's my X, and then I should have list 2. If that's not there, remember you can find it down on the bottom here in these blues. And then once you got it, you can go ahead and hit graph. And if your points don't show up, a quick way to do this, instead of adjusting your window manually, one quick way to do this on your graph is to click the zoom button, and we could go down, and you got two options here. You could either zoom stat, you could zoom to your statistics, or you could zoom to fit the data. Either way, I'm going to go zoom stat and hit enter, and it should zoom in perfectly for you. And you could look to see what these dash marks are for your X and your Y axis. I go to window. See, my X's are counting from 0 to 4, or 0 to 24, and it's counting by 5. So if I go here, this is like 5, 10, 15, 20, and then 24 it ends on. Same thing with my Y's. Y min, so it's kind of goofy, 0.587. So you could have done like 0 to 15 or something like that as well, but they go kind of exact to fit that data. That's just fine. Okay, so I got it graphed. Now it says find the equation of a reasonable line of fit for that data. Okay, so we just talked, I could draw on a line. Let's just kind of estimate this. If I were to draw on a line here, that would look about, I don't know, something like that, right? And actually, I'm going to change my window. I want my Y's to be nice and clean. So I'm going to go 0 to 15. And I'm going to count by 5. So, okay, that's going to make things a little bit easier for me. All right, so if I do this, so here's going to be my, right there, there's my line of fit. I like that. Okay. So if I want to write an equation for that line, what do I need? I need a point and a slope. Okay, we'll define the slope. I know a point right here is 0, 0. And where's another point I could find? I'm going to go over to like 10 on my x-axis. Where is that on my y? That's just above 5, and it's about 6, so I'm going to say this is the point 10, 6, right? And I got the point 0, 0. Okay, so I'm going to use those 2 points to find my slope. So for my slope, I got 0, 0 and 10, 6. So subtract my, well, that should be pretty easy, right? 6 minus 0 and 10 minus 0. So my slope is 6/10, which simplifies to 3/5. And I know a point on the line, so I can write my equation on the line. And I'm just going to use 0, 0. That's much easier for me. So I'm going to say y equals m, so slope 3/5 times x minus x1. Well, x1 is 0, plus y1, which is 0. So I can simplify that. That doesn't matter. This doesn't matter. So it's really just y equals 3/5 x. Okay, so there's a pretty good equation. And what we're going to do is we're going to graph that equation to check it on my calculator, see if it looks kind of nice. So I'm going to clear my ink here, and I'm going to graph that equation I just came up with. So I need to go to y equals to graph an equation. So y equals 3/5 x. So if I want to put a slope in, I usually like to put it in parentheses. So 3 divided by 5 for 3/5. And then x, don't use this green x over here. That's an alphanumeric x. We want the variable x. So I got to hit this variable button. So there you go, y equals 3/5 x. And now I'm going to go back and graph and take a look. Okay, that was pretty good, right? Pretty solid line of fit. So that's how you can always double check. You can look right on your calculator. Well, there's a way to actually find the perfect line of fit, which we call linear regression. And to do that on your calculator, to find the perfect line of fit, what you can do is, it's a part of your statistics, right? Linear regression, finding that line. So I'm going to go back to statistics, and I'm going to go over to my calculations. And right there, linreg, linear regression. And guess what do you think this is? This ax plus b. Yeah, it's like a slope-intercept form. A would be your slope, right? It's the coefficient on x, and b is your y-intercept. See, so here's another form that you're looking at. We haven't even seen this one. So, I went too far. So linear regression, enter. So my x's are my list 1, y's are my list 2. Good. Frequency list. I don't need anything there. All right, let's just go ahead and calculate this bad boy. There we go. So it gave me the slope, right? That's my a. And then my b is my y-intercept, 1.92. So 0.44 is my slope, and 1.92 is about my y-intercept. So I'm going to write that down as well. So y equals 0.44x plus 1.92. So there's like the perfect equation for that line of fit. Let's go ahead and graph that too. Let's see how close it is to my line that I came up with. So I want to go down to the next one here, and I'm going to go 0.44x. So we got a pretty similar slope. Our slope is about 0.6, but then they're starting at plus 1.92. Okay, let's go ahead and graph that line as well. So my line was just a little bit too steep. This is more along the lines that I drew in, right? So the line that I drew in didn't fit my data very well, right? Because this is more along the slope that those points are going. Okay, so it's kind of hard to estimate. That's why they have a linear regression to be able to calculate it perfectly. So what else can we do here? What does it say? What is the slope of the line? And what is the real world meaning? Well, you can go either way. I'm going to go ahead and use the one that I estimated, 3/5, which is 0.6. So what is that real world meaning, that slope, 0.6? Well, it's 0.6, it's rise over run, so it's like time over people, right? So it's like time over people. So what is it, that 0.6? It's 0.6. Oh, I didn't really specify. Let's say this time is in seconds. So it's saying it's like 0.6 seconds per person, right? So it's taking about 0.6 seconds for each person to do the wave. So every time there's a person, it adds 0.6 seconds. Okay, so always think of like your rise over your run, right, when you're trying to find out its real world meaning. It's always like a rate, some type of rate. What about this? What are the x and y intercepts of your line? What are their real world meanings? Well, I could look at the graph, or I could think, remember, the x-intercept is when y equals 0, and the y-intercept is just the opposite, is when x equals 0. So if I think about this, so the x-intercept, when y equals 0. So when the time is 0, so if I did look at my graph, if I looked at that nice line that was drawn, if I went for when y is 0, which is down here, right? So this line would go all the way over. That'd be like negative people. That wouldn't make much sense. In my equation, I'm saying like 0, 0. So at 0 time, like 0 people would be taken to do the wave, and negative people. So really, there's not really much real world meaning with this guy. So for the x-intercept, where it crosses the x-axis, that would be when the time equals 0 seconds. And there's not much I can tell about it in this case. Sometimes you can, but in this, like, the wave hasn't started, so there's no like initial amount of people or anything like that. For the y-intercept, well, now it's the number of people is 0. And what is the y-intercept in our case? Well, the equation that we found, there was no y-intercept, and the one that they gave us was 1.92. So really, it takes 1.92 seconds to complete the wave with 0. So that doesn't even really make sense here. So there's really no real world meanings with my x and y intercepts in this case. A lot of times there are, okay, but in this case there really isn't much. So you just want to state that, you know, the number of people is 0, time is 0 for the x-intercept. And lastly, what is a reasonable domain for this equation? Well, remember, domain are your x values. So what's representing my x values here? Well, that was what? The number of people. So what could I have a negative number of people? No, I can't. So I know I can't go below 0. Could I have 0 people? No, that really wouldn't make any sense either. So let's go, what would be my smallest amount of people I could do the wave? Well, probably one person. So maybe even starting at 0, I can't have like a decimal of a person. So I'm going to start at 1 instead. And I'm going to say less than or equal to x. I could just say x is greater than or equal to 1. Like all my values are bigger than 1. But I couldn't have like an infinite number of people. Like I probably wouldn't be able to do the wave with 1,000,000 people. So what's kind of a reasonable number? I could say is less than or equal to, well, most stadiums fit about, the biggest ones fit about 100,000. So I could say, you know, like 100,000. I'd be okay either way. If you said this, that's probably fine, because unrealistically, you could have as many people as you wanted to do the wave, but realistically, you probably wouldn't have, you know, more than like 100,000 people to do the wave, because they just don't make stadiums that big. So when it asks for the domain or range, it's just asking like what can the x values be, or for the range it'd be what can the y values be. So the nice part about having an equation is that we can make predictions for points that we do not have data for. So for example, it says how long would you predict the wave would take for 18 people? Well, let's go back. Let's use the nice, really good linear regression equation. I don't care which one you use if you want to estimate it or calculate it exact. So let's go over here, and I'm going to grab that equation. It says, how long would you predict the wave would take for 18 people? Well, the people were the x's, so I just plug in 18 for x. So I'm going to say y equals 0.44 times 18 plus 1.92. And when I solve that in my calculator, I get 9.84 seconds. And I can do the same thing for 100 people. I could plug in 100 for x. 100 plus 1.92, and I end up with about 45.92, so about 45.92 seconds. Okay, and we have terms for that. So if you notice this 18, if I go back and look at my table, 18 fell inside of my data, right? If I were to look at my graph on my calculator again, that 18 actually appears on my graph, somewhere in that range right there. So that's actually on my graph. But that 100 is not. And we have terms for that when you look for something inside your data and something outside your data. So the 18 is represented by what we call interpolation. It says using an equation to help us predict values for points that are between points we already know. And I always think it kind of means inside. So when you look for something that's inside your data already. Whereas extrapolation, that was when we solved for 100 people. That was outside of my data, right? Extra, I think it's like extra beyond the points that we already have. And so you got to know what those terms mean. So just key on the inter and the extra. And in this green down on the bottom, if you notice, it says this can be misleading if we don't have enough data or an incorrect equation. So that's why it's important to have a correct equation, and that's why that linear regression is super nice, because it gives us an exact equation. But we can always come up with our own line of fit for it. And if you don't have enough data either, it's usually not very useful. Okay, so those are some things to key on.